Alright, hi guys, Jim Caffey here, and this week we're going to cover chapter 19 in our Cosmic Perspective book on our galaxy, the Milky Way. Here's one picture of our galaxy. Oops. So here we can see our Milky Way galaxy in the night sky. The dark bands you see in there are actually dust bands that cover up the light. And this is part of the interstellar medium that makes up new star systems. It takes dust and gas to make new stars. There's so much dust in the Milky Way galaxy that if we removed all the dust out of it, you would actually be able to read a book just from starlight. So here's a schematic of our galaxy. We see our galaxy edge on, and there are some features to it, such as the disk, the flat part, the bulge in the center, the halo, which is kind of like the suburbs all around it. And in the suburbs, we have these little cities called globular clusters, which have many very old stars. And now the sun's location is right here, about 27,000 light years from the center. This galaxy, the Milky Way, is 100,000 light years across and about 1,000 light years tall, the disk. And in the middle is a bunch of dust. And we call this a spiral-barred galaxy. If we could see the Milky Way from above the disk, we would see its spiral arms. And these spiral arms are where energy waves are that create new star formations. And then surrounding the galaxy are these globular clusters, very spherical with lots of old stars in them. Whereas in the spiral arms you have new star formation and they're blue. So the stars in the disk of the galaxy all orbit in the same direction with a little up and down motion to it. Whereas the orbits of the stars in the bulge and the halo have just random orientations. So to summarize, the halo stars travel above and far below the disk in orbits with random orientations. So do the bulge stars, they're random, but the disk stars orbit in circles with the same orientation except for just a little bit of up and down motion to them. Now high mass stars have strong stellar winds that blow huge bubbles of hot gas into space. Lower mass stars, like our Sun, return gas to interstellar space through stellar winds and what we call a planetary nebula. And that's what this is. This is something similar to what will happen to the Sun in about 5 billion years. We'll form our own planetary nebula with a little bitty white dwarf dead star in the middle. Now, of course, we can look at stuff in other dimensions. We can look at X-rays, and so X-rays from a hot gas and supernova remnants, stars that have just completely blown themselves to pieces, reveal newly made heavy elements. And this is really where everything except hydrogen and helium come from. The calcium in your bones, the iron in your blood, that all comes from supernova explosions. So we like to say that we are made up of stardust. That's really true. A supernova remnant cools and begins to emit visible light as it expands, and these new elements made by a supernova mix into the interstellar medium. Gravity forms stars out of the gas in molecular clouds, completing the star-gas-star cycle. And here is a nebula where we have these little nodules here. We call these eggs, and we call these gaseous globules. And so these are where new stars are being formed. Now, of course, we can observe the star cycle, all the different wavelengths operating in the Milky Way's disk using different wavelengths of light, from radio to infrared, visible, X-ray, and gamma rays. So let's take a look at a few of these. We'll compare them to the visible, we saw before here. 21 centimeter radio waves are very particular because that's what the kind of radio wave emitted by atomic hydrogen. And so we can look at the pure element of the universe, hydrogen gas in the atomic state, where the gas is cooled and settled into the disk. In the radio waves, we see carbon monoxide, show the locations of the molecular clouds. Infrared shows us dust. Longer wavelengths infrared emission shows where young stars are hitting dust grains. Infrared light also reveals stars whose visible light is blocked by the gas clouds. X-rays, however, are observed from hot gas above and below the Milky Way's disk. And finally, gamma rays show where cosmic rays, these atomic particles from supernovas, collide with the atomic nuclei in gas clouds. And so much of the star formation in the disk happens in these spiral arms. It looks very similar to a hurricane, I always thought. And you know, even in a hurricane, you have an eye in the middle. Well, in these spiral galaxies, most of them have a massive black hole as an anchor. And this is M51, Messier 51, the Whirlpool Galaxy, very face-on spiral massive galaxy, about 50 million light years away. And the fact that we can get an image like this from the Hubble Space Telescope 50 million light years away is pretty spectacular to me. So the spiral arms are waves of star formation. And how did our galaxy form? Our galaxy formed from a cloud of intergalactic gas. Halo stars formed first as gravity caused the gas to contract, and the remaining gas settled into a spinning disk. Now this is a very simplified model, but the stars continually formed in the disk as galaxy grows older. And in the center of our galaxy is that central object, a massive